Good morning, everyone. Those of you at the back, can you confirm if you are hearing me? Those of you at the back, thank you so much. I want to welcome you to another applied multivariate statistics class. Of course, statistics is like a story that goes on and on and on. Today, or let me just say specifically this week, the focus is going to be on chapter 3. Of course, you can find all what we've been doing in the recommended textbook, and I believe you all have access to that on Canvas because I share the electronic version of the textbook on Canvas. So, the focus this week is actually on chapter 3, that I call sample geometry and random sampling in multivariate analysis. Let me just review a background. I just want to talk about, remind you of what you've done, uh, before this class, that make you to qualify to take this course. I want to believe you've offered theory of statistics, whether 5101 or 4101. And let me quickly remind you, because there's a kind of linkage between 5101 that I call the theory of statistics and what we want to be doing now. In theory of statistics, we actually focus on random sampling that has to do with univariate. When I say univariate, we're focusing on one measurement at a time. We understand how uh, you know a sample mean, the sample variance, the sample standard deviation behaves. Of course, I remember um, in the theory of statistics, you're familiar with the law of large numbers. That's actually going to tell you that when the sample size increases, we expect the sample mean of the univariate data, to converge to population mean. And of course, we also expect the sample variance to converge to population variance and stuff like that. But let me tell you what we want to do today. We want to take that to a new level where we are no longer going to be talking about the behavior of sampling, of random sampling in in a single dimensional space, but we want to extend that to high dimensional space. So what we want to be doing from this week is actually to walk you through how we can have an understanding of how random sampling behave in high dimensional space. And of course, why is it called high dimensional space? Because we got so many features involved. And of course, when we have so many features, of course, that's high dimensional. And we're actually curious to know how random sampling behave. And the moment we know the way random sampling behave, we'll be able to have an understanding of the data structure. When I say having an understanding of data structure, I want to have an understanding about the shape of the data structure. I want to have an understanding about the spread. I want to have an understanding about the orientation and so on, like that. So because of that, I think I want to welcome you to sample geometry and random sampling. Okay, so this material, 49 pages, is what I'm actually going to walk us through, what we're going to be going through this week. So uh, this is the outline. In the outline, I'm going to talk about the motivation, talking about the variable space, observational space. Okay. Now, I just wanted to take note of this. There's a difference between variable space and observational space. Don't forget your multivariate data set is in terms of a matrix where you have observations arranged in row and you got features arranged in columns. Okay, so we actually going to be talking about space occupied by observation. We're also going to be talking about space occupied by different kind of variables or features you're using. Now we're going to focus on the mean, the covariance. Don't forget the other time, our intention is to understand the data structure. Understanding the data structure, we want to have the knowledge of the average. We want to have the knowledge of the spread, and we want to have the knowledge of the shape. Okay, all of that become very necessary. And of course, believing if we have a covariant structure, we'll be able to achieve that. Okay, so we're also going to have a global summary statistic. Okay, for S. When I say S, I'm actually talking about the sample covariance. Okay, so we're going to talk about all of that. If you want to read it, okay, read the chapter 3 from the recommended textbook. Now let's get started. You know, what we're going to be doing today is very, very essential. And of course, is very linked to every other topics that we're going to be focusing on. Now, let me tell you this in general. You know, what the sample geometry we provide, you know, is actually going to provide us with understanding of how random sampling behave in a high dimensional space. I'm going to say that again. Sample geometry, okay, will enable us to understand how random sampling behave in high dimensional space. In your 5101, in the theory of statistics that you did en route to this course, of course, you're familiar with a random, you know, random sampling in one dimensional space, you know, where you learn about the idea of how sample mean changes from sample to sample. You learn idea of sample covariance, you know, sample variance also changes as well. Okay, and of course, you know the reason why sample mean changes, why sample variance changes is because the sample mean is a function of observation. Okay, and the observation, you know, that we're talking about, you obtain that randomly. So sample mean is actually random because it's a function of a random observation. Okay, that is the bottom line. And of course, the sample variance as well also going to be random. Okay. And that, you know, when I say random, you know, when you collect different data set, you're actually going to get different sample variance. Okay, that's exactly what I mean. But in a multidimensional space, okay, we're actually going to be talking about mean vector. We're going to be talking about sample covariance, and we also want to see how, you know, sampling, I mean, how random sample is actually going to behave, because we also expect mean vector to vary from sample to sample. We also expect sample covariance to also vary from sample to sample. Okay, which means we want to have an understanding of, you know, how sampling distribute, you know, I mean, sampling, random sampling behave in high dimensional space. Now we got three basic statistical measure of importance, which I call the sample. You can say the mean, okay, which is the sample mean vector, the sample covariance, and the R is actually the correlation matrix. Now, in the high dimensional data, okay, well, we actually the basic statistical measure that we want to obtain are these three. Okay, so now I just want to tell you this. All these three have their geometric interpretations. I'm going to say that again. They have their geometric interpretation. And let me tell you this, when I say geometry, here, can we have a way to turn linear algebra or matrix algebra into actionable insight? What do I mean? Turning that into actionable insight, we actually want to have a way to connect these three basic measure to the data structure. I'm going to say that again. Of course, these three basic measure, where do they come from? They come from data, right? They come from data structure, right? We want to have a way to link them to the data. And that's why I said here, we want to study this relationship, okay? And believing that the relationship, will provide us an insight. Don't forget from day one, well, what's our intention from day one? Our intention is to be able to extract meaningful information from the data set. And when you are working, let me say this. You want to extract meaningful information from data set using statistical model, then you need to be able to understand your data structure. In this class, our focus is on multivariate data. Okay. When you have a multivariate data, okay, how are you able to provide an actionable insight, okay, depends on how you understand what is going on in high dimensional space. If you don't understand what is going on in high dimensional space, of course, you may not be able to, explain relationship. How will you explain relationship when you don't understand what is going on? And that is exactly what we're trying to do here. Okay, and I said we introduce a summary statistic. When I say summary statistic, I'm actually referring to these three, okay, because we have two types of statistics generally. We have a descriptive statistics, we have inferential statistics. So in descriptive statistics, we use these three basic measure, okay. And let me tell you this. I said introduce a summary statistic that describe the variability in the data. Let me tell you this. We actually want to understand variability in the data set, and to be able to understand that variation, the idea of geometry is required. And that's why we need sample geometry. The sample geometry will provide us with that very understanding. And let me tell you this, okay? Going into this, I'm actually going to say we're going to have some assumptions. I told you from day one, okay, whenever we specify a model in statistics, okay, uh, we have assumptions. We have assumptions that revolve around the error in the model, because what make a model to be great is when uh, assumptions are met. So if we really want to understand the structure of the data set, okay, in the multivariate data set, for you to be able to have a kind of idea of what is going on, okay, of course, we need to fall for, since we're going to use the module to do that, the module we're going to use to do that have assumptions, okay, and assumptions need to be made. And what are the assumptions here? Now let me tell you this. The sample geometry here, we assume that the data point that we have, every data point that we have in a multivariate analysis is actually a vector, okay, in p-dimensional space. I'm going to say that again. Okay, the sample geometry is actually viewing every observation as a vector in a p-dimensional space. I'm going to say that again. When you have an observation, let's say observation number one, this person, okay, it's actually going to be viewed as a vector in a p-dimensional space, because that particular observation is collected across so many variables. Maybe in a clinic, I have a patient where the doctor measured the height, the weight, the blood pressure, and so on like that. When you take a look at that very row, okay, each observation, don't forget, each observation occupy a row in a multivariate data set, and that very each observation is assumed, to actually have a vector in a p-dimensional space, and we actually call that a cloud point. Okay, we call that a compound, and that's why I said each row of the data is on, and they have to be unrelated of others. Okay, they have to be unrelated. Of course, one of the essential assumption in statistics is independence of observation. Okay, they have to be related of the others, and not only that, each row corresponds to a case, can be an individual, it can be a sampling unit, and of course, you're not going to have this data structure. This is the data structure we're talking about. That is the data structure that we're talking about. N observation by P numbers of variables. Okay, so you've seen this assumption number one. Now let's talk about assumption number two. Assumption number two now is that the joint distribution of P variables is the same, for all observations. Okay, we want the distribution to be identical. I don't know whether you've heard about identically and independently distributed random variables. Okay, so the joint distribution of P variables, has to be the same. Okay, for all cases. Okay, now that is those are the assumptions. So you've heard about the assumption now, and let me tell you this. Since you've heard about this assumption, let's now go into variable space. The In a variable space, what do I have in a variable space? Okay, I believe, okay, we have observation forming a cloud of data. Observation actually seen as a vector, okay, in P dimensional space. Okay, that's what happened in the variable space. And of course, we define the variable now that we're talking about as an uppercase X. When I say an uppercase X, I'm actually saying, oh, I got more than one features, okay? And of course, that would define the axis, because when I'm talking about geometry, there should be axis. So what form the axis now is actually the variable. Okay. Now, which means we are now considering endpoint of that. When I say endpoint, talking about a number of observation, could be number of cases, okay, in the p-dimensional space. And let me tell you this, when that happen, okay, I can begin to obtain the three basic measures that I talked about the other time. I actually want to know what is the center of this particular S. Okay, what is it? Well, what is the center I'm actually mean? What does it mean? I want to know the mean of the height. What is the mean of the weight? What does it mean? What does the sample mean of each variable? Okay, in the variable space. Okay, and that's what I call the center of the point. Okay, which is the X bar. Okay, we also call it centroid. Oh, give me 1 second. I'm actually gonna write this down. Okay, we also call it centroid. We call it centroid. Okay, we call it centroid. Okay, we also call that centroid. And let me sorry, we also call that like a center of mass. I remember in physics when I was doing the center of mass or the center of gravity or something like that, because I know there's variation, but I'm actually interested in a particular data point that can potentially represent others. The way politicians represent a particular consistency in the house. Okay, now let me tell you this. Whenever center is involved, whenever mean is involved, whether in univariate or multivariate, then we also need to talk about variability. Because the center that we have, how am I going to know whether the center is doing a great job? How am I, because the center is expected to represent others? How am I going to know that it's doing a great job? Just like politically, how am I going to know if a particular representative or legislator is doing a great job in the House? That particular legislator must be very close to his or her constituency politically. And that's why they conduct town hall meeting and so on like that. We also expect mean if the average is actually representing data set, we expect the average to be very close, okay, close to the other observations. Okay, if I want to measure that, I'm talking about variability. So as I said, variability and covariability will be measured by S because when I say variability, there's going to be variation within a particular variable under investigation. I can also measure the covariation. I can also see how variables in a multivariate data set, how they varies together. That's why you see covariability. And that's why this guy is going to be doing a job of actually measuring that. And that's why in the covariance matrix, when you look at the diagonal of a covariance matrix, you're actually going to see the variances that is within variation, within the variation within a particular variable, maybe the variation within height, within weight. Okay, but when you look at the half diagonal, we talk about the variation between. Okay, variation between height and weight and stuff like that. Okay, now please I need you to pay attention. And I want to have a variable space example now. Okay, if you take a look at what I'm showcasing now, this is 9 by 2. It's like I have 9 persons and I only collected, the data over just two variables. Okay, the column represents the variable. As you can see, right now, this guy is actually represent the first variable. This guy represent the second variable. If I want to go by this, by row, then I'm actually having 9 observations. And that's why this is actually called 9 by 2. If I want to have a way to understand, if I want to understand this the more, okay, I can actually provide a geometrical representation, okay, where I'm just going to plot them. This is the plot. Take a look at what I have right now. Okay, this is the plot here. Look at that. Oh, where's this 0, 0? Okay, 0, 0. Can see here? That's where 0, 0 is. Okay, so where's 1, 1? Can you see that? That's 1, 1. Okay, I'm plotting this here. Take a look at that. Okay, this is two-dimensional. If you take a look at what I have, because I have two variables, okay? But let me say you this. If I have this, I actually want to compute the sample mean vector. Don't forget, the very first, the first thing we want to have the idea of is the center of the cloud, which actually calls sample mean, okay? And of course, I'll take a look at what I have here now. This is just like, oh, what does it mean of this guy? What does it mean of that guy? That's what we have here. Can you see that? That's what we have here now. Okay. So, and I said, what happened to the picture if we multiply x by 2? Okay, maybe I don't know. Of course, you in your high school, I think you've done something that has to do with horizontal stretching, vertical movement, stuff like that. You're also going to apply that here. Okay, moving upward, moving downward. Of course, something that has to do with the vertex, stuff like that. So now. We've talked about the variation of the variable space the other time, and I want us to talk about the observational space. Okay, and let me tell you this: both variable space and observational space are represented in your data structure. Okay, now take a look at that. I said alternative geometry representation of S that consider the data point as speed points in n-dimensional space. Now, this is what happened. Okay. How do I view individual observation? Okay. Okay. If I want to do that geometrically, I view individual organization, I'm actually going to ask, it's going to be the one that will define the axis. Of course, when you're talking about geometry, we talk about axis. We talk about the direction of axis as well. Okay. All of that we take a center stage when by the time we start principal component analysis, okay, where we may want to understand the length of the axis, we may want to understand the direction of the axis and so on like that. Okay, so that's what you see. Okay, the dimension of the space. And of course, you can see the S is a vector in the n space. Okay, here we are defining the observational space. Okay, now there's something I also wanted to see. Okay, I can actually do this. I can call the whole of this something. Okay, maybe I'm gonna call that this. I can call the whole of this. So let me do this for that, for that, all the way to the P. Okay, because each of these variable has observation in them. Okay, it has observations in them. Okay, and of course, oh, this is a simple way of actually representing that. Now I'm actually moving. Now take a look at this guy now. I'm having more than one dimension, more than two dimension now. If you take a look at what I have here. Oh, I only collected response from only two individuals, but the variables that I have is four. That's why you see 2 by 4. Two observations against four variables. And if I want to represent this geometrically, of course, I'm actually going to have so many lines. Look at that. Can you see what I have now? Can you see y1? What is going to serve as y1? Please pay attention. Okay, if you take a look at this, this is my y1 now. That's what I plotted here. Look at that. 4. Can you see that? Against 0. Can you see that? That's my y1. Okay. This is my y2. Can you see my y2? That's plotted against 1, 1, right? That's all like that. We're having a multi-dimensional space here now. Okay, this is an example of high-dimensional space. High-dimensional data because the number of features is more than the number of observation. And let me tell you the situation where this happened. There's possibility. There could be some instability with regard to the covariance structure. The covariance structure that you're going to obtain may be unstable. And that's why we need to be able to think of having a robust multivariate approach to deal with the situation. Okay, I just wanted to see that. We're doing this geometrically now. Now, please pay attention. I want to come into the basic measure now. Let me tell you this. Uh, in the univariate statistics, we have law of like number. Before that, we believe when we collect observation from a normal population, okay, or not, essentially, I'm sorry, the law of like number actually enable us to understand that sample mean converges to population mean, right? Now, how do we also have stuff like that in high dimensional space? Yes. Sample mean vector, okay, converges to population mean vector when the sample size increases. So law of like number also take a center stage in high dimensional data. Okay, and not only that, uh, you know, we also expect some kind of stability when it comes to covariance structure. We expect the sample covariance as well to converge to around the population covariance structure. There is sample covariance, there is population covariance. The population, whether population covariance or population mean, they are the true value. All our effort is to estimate the true values. And we believe by law of large number, whether you are dealing with the univariate situation or you are dealing with the multivariate situation, in as much your sample size is large, number of observation is large, whether in high dimensional data or in a low dimensional data, we expect the sample mean vector to converge to population mean vector. We also expect some kind of stability of the sample covariance structure. Now, let us now look into the mean. Now, one of the basic measure. Now, if I want to talk about the mean, the mean that I want to get, the number of I only need the number of observation to figure out the mean within a particular variable. I'm going to say that again. I need the number of observation, okay, to figure out what the mean is within a particular variable, within a particular, maybe height. Okay, if talking about height, if I want to find the mean height, then I need to add the height of every person. Does that make sense? That's what I mean. Then divide by the number, and that's exactly what. Now take a look at this question. How does sample mean relate to the vectors in the observational space? Okay, we want to see how sample mean relate. Don't forget the other time, the one of our intention here is actually we want a sample geometry to provide us an understanding about how sampling how random sampling behave. Okay, if you want to know how random sampling behave in a high dimensional space, you need to first understand how does the sample mean relate to the vectors in the observational space. Oh, sample mean, how does it relate? Oh, sample mean, statistically, sample mean is a function of observation. Why? I need to add observation and divide by n to get the sample mean. That is the relationship that we're talking about. Okay, but we want to look at that geometrically. How? Let's take a look at that. Now, if I want to answer that question, this is the question. That means the projection of the vector variable into one. You have a vector. Why do I say one? That means one, one, one. Oh, they have equal weight. Oh, they have equal weight. That is why I'm adding all of them together and divided by n. Which means in what we've done before, you are oh my God, you are assuming equal weight to all the observation. That's why you are adding them up and you are dividing by n. Does that make sense? If you have a value for this observation, maybe I have a weight value for this person. I'm believing that the probability is the same for every individual. And that is why if I add them up, I divide by n. We don't just do what we do. We have reason why we do what we do. So that is how the sample mean is obtained with the intention that all the observations have equal weight. And if I want to talk about that geometrically, then I'm actually saying we are projecting the vector variable into ones. When I say one, if you take a look at this guy, one mean one. This variable, this weight, the weight of each observation is the same. One, 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 and so on like that, depending on the number of observation that we have. That's why you see this. That's why we say one subscript n. Is there any question on this? Let me tell you this. I understand my mathematics, my statistics perfectly because I'm able to relate to real life. If you don't relate, if you don't understand each notation, if you don't understand reason why you do what you do, the math, the statistics, it's not going to make sense. Okay, now let's see. We now because of that, because we mentioned projection, now we want to see how projection work. How does it work? Take a look at this guy. Okay, I now because I want to understand the projection of vector into ones then I need to for of us understand what how do we say something project into something. Now, because of that, I want to talk about the projection of x into y. Okay, projection of x into y mathematically. This is it. It's going to be, you can now see when I was having a math review the other time, or when I was, I mean, last week, we talk about cross products. You can see S prime Y, the inner product. We're using that now. Okay, you see Y prime Y. That is a formula. Okay, and when you take a look at this formula now, please pay attention. Okay, this guy is this guy here. This guy is this guy here. Okay, and do you know if I have this guy, if I have each of that, I'm just talking about the length of a vector. The length of a vector in a square form. Y prime y is the same thing as summation y square in statistics. And geometrically, it's talking about the square of the length. Look at that. Okay, now I'm actually moving now. Please pay attention. I'm moving. Now, and let me tell you this. Hmm. Do you know that we actually talking about this guy, projection of S onto Y. When you're talking about projection of S onto Y, and we got S star, okay? This is the S star, okay? And of course, we also need to consider the length of S. And whenever that is involved, we're going to talk about there's going to be an angle between vector. Why is it that the angle between vector become necessary? Do you know that in multivariate analysis, where we got so many variables, okay, situation, the angle between two variables have interpretation. If the angle is 90, then they are orthogonal. Okay, if angle is 90, okay, or 90 is like probably they are unrelated. If angle is if the angle between them is very close to zero, then they are positively related because the angle between them very close to zero, they go together. That's what it means. Does that make sense? So we can have a we can also measure when angle is 180. Oh, it's like they are inversely related, stuff like that. So angle has meaning. Okay. Now, whenever you're talking about projection, of course, we are vectors. We also need to talk about the angle between the angle between them. Okay. Now I'm moving, and I want to go back to the mean that we're talking about. I said the other time we want to project the vector onto one, right? Let's define the 1, 1, 1, 1. Want to define the 1, 1, 1, 1 is this guy. The 1, 1, 1, 1 is going to be n by 1. Okay? Because that's like a weight. For each observation, they are equally weighted. That's what it means. Equally weighted. Okay. Now let's take a look at the variable that we want to project, the vector that we want to project. Oh my God, is this guy here? We are projecting this guy into that. We are projecting the vector, okay, the transpose of that vector. Why do I put a transpose? Because I want to write it as a row. Initially, it was a column vector. Does that make sense? If you take a look at what I have now, I'm putting a prime, right? That's a transpose, making it to be a row because my projection, my vector has to be in a row before I can do that. Don't forget, I also need to put into consideration, confirmability of multiplication. When I want to multiply matrices, we don't just multiply vector or matrices. We need to be guided. Okay. Now, uh, if you take a look at what I have now, okay, if I take you back here, when I was doing that to x and y, okay, please pay attention. When I was doing that to x and y, s onto y, this is the formula. But now I want to do that, okay, for y vector into ones. Now, look at this, and I want you to see what is going to change. Please pay attention. Are you looking at that? Something is going to change now. Let's see. Oh my God. Can you see the formula now? Look at what is happening here. I'm projecting y vector into ones. That's why you're seeing this guy here into ones. Can you see that? Now, when you're now doing that, when you're doing that, okay, you have this ones, this guy. Can you see that? Okay. And you have this guy. Okay. Of course, in the denominator, okay, if you take a look at this guy here, in, one, please pay attention. One n, okay, one n is this guy. One, one, blah, 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 until we get to one. If I now do the if I now do the transpose of that, okay, oh sorry. Uh Now if I do the transpose of this guy is gonna be a row, right? One. It's gonna be one, one, blah, 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 until I get to one. Okay. And you know what this guy is saying? I should start multiplying. Oh, one times one. This one times one times one, until I get a one times one. That will still be one, 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 one. Then I'm going to add them up. One plus one plus one plus one. If I have five observation, sorry. If I have five, oh yeah, five observation, that will be five. If I have n observation, that will be n. And that's why we have n here. Look at that. And here, this guy is multiplying that. That guy is multiplying that all the way to this guy. That would be summation S. That would be sum of S. Now, in the hand, oh my God, in the hand, you have your mean. Okay? In the hand, if you take a look at what I have right now, let's pay attention. If you take a look at this guy, that give you the mean. Okay? And this guy. Now, why do you think we have this guy? We have that guy so that you can have it as a mean vector. Does that make sense? So that's why. Is there anyone who doesn't understand this? That projection? Is there anyone who doesn't understand that? Okay. Silent implies that you understand it. Then I'm actually moving. I'm gonna move right now. Let's move to something else. Okay. Mean, we now want to discuss what we got. Okay. The mean in the observation of space. And take a look at this. We have projected y vector onto one vector. And that was why, because of that, I'm actually making this statement. Take a look at this statement here. I said the sample mean of the that x bar k of the kth variable. Don't forget, we got several means for each variable, right? Okay, if I want to talk about the one for a particular variable. Now that corresponds to multiple 1n required to give the projection of yk onto the vector 1n. Okay, so that's what I mean. Now, and whenever projection is involved, don't forget there's going to be an angle. It's going to happen this way. Take a look at that. Okay, this is this, this is that. Okay, so now you are initially, this is I wanted to see the direction. I want to see this yk 1n. Can you see that? And this was the sample mean vector, that we got. Okay. Now let me tell you this. If I have a sample mean vector, do you know I may actually want to look at the difference between observation and the mean, and that is going to give me another vector, and that very vector will be called a deviation vector. Take a look at this guy now. Hmm. Deviation vector now is, oh, I'm subtracting the mean that I got, from each and every observation in that particular uh, variable. We call that a deviation vector. And let me tell you this. Why do I need deviation vector? Oh, if I don't get deviation vector, there's no way I will be able to get the covariance. You remember what we did the other time? The covariance is actually where the deviation vector is the one I call centered. Centered data where you have SC transpose SC divided by N, okay, without the deviation vector, you may not be able to do that. But let me tell you this, because of this, mathematically speaking, because of this, if I want to make this guy the subject of the formula, the original observation, the subject of the formula is going to be this guy plus that. Okay. Now, because of that, I'm actually going to say something now. Please pay attention. Okay. I'm actually saying this. Take a look at this. Because of that, I'm going to say this. I'm actually seeing, and that was the reason why I said the other time, every data set is contaminated, which means we can, if I want to, I can do something by decomposing. This is like decomposing my YK into two different parts, into the mean and the deviation from the mean. The deviation from the mean is actually the difference between, something I will talk about the other time. So take a look at that. Now, if I'm saying this guy as this guy, then don't forget this guy is this guy here. Okay, automatically, mathematically, you're going to see something cancel out. Okay, this, cancel this out. So I have this, which is that. So that is the decomposition that we're talking about. Okay, like I said, this material, we're using it for this a whole week. Okay, this same material. Okay, I think what I'm going to do is okay, let me explain this before I go. Now take a look at this, and I need you to pay attention. Okay, now if you consider the direction of 1 1, what does it mean? 1 1. 1 1. Well, maybe I have two persons or two individuals or two cases or two observations. Okay. Now, if I want to do that 1 1, okay, but I have four variables, two observations, four variables, as I did mention, I'm actually going to have this picture. Take a look at that. This is the geometry. Look at that. Okay. And in that case, how do I find the mean for each variable? Oh, if I want to find the mean for each variable, how many observations do I have for each variable? Oh, I got two for each variable. Okay. And for each variable, for each observation within a variable, I'm actually using 1 1. I'm using equal weight. Don't forget equal weight. Now, because of that, that's why you see I multiply because the 0 and 4 that you see here. Give me 1 second. Some of you may be wondering how do we have 0 and 4 and stuff like that. Let me go back to the data itself. I'm using this. Can you see this guy? This is what I'm still using. I'm still using this. Can you see that? We got two observations, four variables. Okay. Now, how do you find the mean? Using the idea of projection. Okay. The mean is just 0 plus 4 divided by 2. But how do I get 0 plus 4 divided by 2? It's right here, because I'm assuming equal weights, 1 1 to each person, okay, within a particular variable. And of course, when I do that for each of that, this is the mean for each. And that's give us the mean for each. Is there any question before I go today? Let's note where we stop today. We stop at page 12. On Wednesday, we're going to start at page 13, slide 13. We're using the same slide for the entire week. Of course, Wednesday, I think I made an announcement. And I changed that. So Wednesday, we're not meeting in person. It's gonna be on Zoom. So I will expect everyone. We're not meeting here on Wednesday. So we're meeting on Zoom. Okay? So that's all what I got. I sure you all stay safe and have a lovely day. Bye for now, everyone.